Right now, a spacecraft older than most of your parents is sitting more than 13 billion miles from where you are reading this, and it just forced scientists to admit that something they were sure about for 6 years might have been wrong. Not a small correction, not a rounding error, a real documented, published reversal of what we thought we understood about the edge of our own solar system. It happened because a second machine, launched 16 days before its more famous twin, finally reached the same invisible wall in space and saw something different when it got there. This is the story of Voyager 2, and by the time this video is over, you are going to understand why the data it sent home didn't just add to what Voyager 1 discovered. In some very important ways, it rewrote it. I'm your host, and this is Verge. If you're new here, we tell the stories about science and discovery that sound too strange to be real, except every single one of them is. And this one might be the strangest yet, because it involves two identical machines, built by the same engineers, launched weeks apart, that ended up telling us two different versions of what lies beyond our sun's reach. Stick with me, because the part of this story that nobody talks about, the part buried in the actual research papers instead of the headlines, is coming later, and it changes how you should think about the boundary that protects everything alive on Earth. Before we get there, hit subscribe, because we are just getting started, and there's a lot more of this kind of story where this one came from. Let's rewind to the beginning, because to understand why Voyager 2 mattered so much, you need to understand what Voyager 1 had already claimed, and why that claim was shakier than most people realize. Voyager 1 and Voyager 2 launched from Cape Canaveral in 1977, just over 2 weeks apart. Voyager 2 actually went first, lifting off on August 20th. Voyager 1 followed on September 5th, but took a faster, more direct route. So despite launching second, it has always been the one further from home. Both spacecraft were built for the same modest mission. Fly past Jupiter and Saturn, take some pictures, gather some measurements, and then fade quietly into the background of space history. Nobody, not the engineers, not NASA's leadership, not the scientists who designed the instruments, expected either machine to still be transmitting data back to Earth nearly 50 years later. And yet, here we are. Voyager 1 took the shorter path, and used the gravity of Jupiter and Saturn to slingshot itself out of the solar system faster than its twin. Voyager 2 took the long way around, using its own set of gravity assists to visit Uranus and Neptune as well, becoming the only spacecraft in human history to fly past all 4 of the solar system's giant planets. That detour meant that Voyager 2 has always trailed behind Voyager 1 in terms of distance, but it also meant something else, something that would end up mattering enormously once both spacecraft reached the true edge of the solar system. Because of a small mechanical failure decades earlier, the two machines would end up seeing the same boundary in almost completely different ways. Here's what that boundary actually is, because you need this to understand everything that follows. Our sun is not just a source of light and heat. It constantly blows out a stream of charged particles called the solar wind in every direction, and that stream inflates a massive bubble around our entire solar system called the heliosphere. Every planet, every moon, every spacecraft we've ever launched sits inside that bubble. The outer edge of it, the place where the pressure of the solar wind finally gives out and the pressure of the galaxy's own interstellar material pushes back from the other side, is called the Heliopause. Crossing it means leaving the region of space our sun controls and entering the space between stars. It is, in the most literal sense possible, the edge of home. In August of 2012, Voyager 1 became the first human-made object to cross that edge. It was a genuine historic milestone, and it made headlines around the world. But here's the detail that almost never makes it into those headlines, and it is the detail this entire story hinges on. Voyager 1's plasma science instrument, the specific piece of equipment designed to directly measure the density, temperature, and speed of the charged particles around the spacecraft, had stopped working back in 1980, more than 3 decades before the crossing even happened. It failed during the encounter with Saturn, long before anyone even knew there would be a heliopause to cross. So when Voyager 1 actually reached that boundary in 2012, scientists didn't get a clean, direct reading of the moment it happened. They had to work it out indirectly, using a completely different instrument, the plasma wave instrument, which can only detect plasma density when something disturbs it, like a shock wave from a solar eruption rippling outward and causing the plasma to oscillate, almost like striking a bell to hear its pitch and figure out what it's made of. The problem is, you can't just strike that bell whenever you want. You have to wait for the sun to do it for you. And so, even though Voyager 1 crossed the heliopause in August of 2012, scientists did not get a clear plasma reading confirming it until October of 2013, more than a year later, when a solar outburst finally reached that far out and rang the plasma like a bell one more time. For over a year, the exact moment and nature of that crossing was argued about, debated, and pieced together indirectly. It was historic, but it was also incomplete. And that incompleteness left an open question hanging over the entire discovery. Was what Voyager 1 saw actually representative of the true edge of our solar system? Or was it just a one-time snapshot, specific to the exact place and moment that one machine happened to cross? That question sat unanswered for 6 years. And then, in November of 2018, Voyager 2 caught up to that same edge at a different location, moving through a different part of the boundary, and this time, its plasma instrument was still working perfectly. This is where the story stops being just a history lesson and starts being something scientists genuinely did not expect. Because when Voyager 2 crossed the Heliopause, there was no year-long wait, no need for a solar flare to ring the bell from a distance. Its plasma instrument recorded the crossing directly, in real time, the way you'd want a scientific instrument to actually work. And what it recorded was almost shockingly abrupt. The density of charged particles around the spacecraft jumped by a factor of roughly 20. Within a stretch of space so small, researchers measured it in a fraction of an astronomical unit, over in what amounts to a cosmic blink. Scientists had modeled this transition as something that should happen gradually, a slow fade from one environment to the other. What Voyager 2 found instead was closer to a wall, a sharp, clean, almost instantaneous shift from the hot, sparse plasma of our sun's bubble to the colder, denser plasma of interstellar space. And here's the part that should stop you for a second. Voyager 2 also measured something Voyager 1 never directly could, the temperature of the plasma right at the boundary. And it came back somewhere between 30,000 and 50,000 degrees Kelvin. That's hotter than 50,000 degrees on the Fahrenheit scale in some readings, in a region of space that models predicted should be relatively cold and calm. The leading explanation researchers have offered is that interstellar material is essentially piling up against the outside of our solar system's bubble, compressing and heating as it presses inward, the same way snow compresses and warms slightly when a plow pushes hard against it. It's not that interstellar space itself is that hot. It's that the boundary layer, squeezed between two competing forces, behaves like nothing the models predicted. So now you have two spacecraft, 6 years apart, telling two versions of the same crossing, one inferred indirectly, uncertain in its exact timing, and unable to measure the boundary's temperature or density directly at all. And one measured cleanly, in real time, revealing a boundary that was sharper and hotter than anyone had modeled. This alone would be enough to justify going back and re-examining what Voyager 1's data actually meant. But it's not even the biggest surprise. That one is still coming. Before we get to it, I want to ask you something, because I'm curious how many people watching this have ever actually thought about how strange it is that we have real living data from outside our own solar system at all. If you had to guess, before today, did you know humanity had two working machines out past the edge of the sun's influence? Or did you think that kind of thing was still science fiction? Drop that in the comments. I read every one of them, and I'm always surprised by how many people had no idea this was actually happening in real time right now while we go about our normal lives. Now here's where it gets stranger, and this is the part almost nobody outside the actual research papers ever talks about. For decades, one of the most basic predictions scientists made about the heliopause was about magnetic fields. Inside our sun's bubble, the magnetic field is shaped by the sun itself. Outside it, in true interstellar space, the magnetic field belongs to the wider galaxy, and it should, according to every model built before either spacecraft got there, point in a noticeably different direction. Crossing the boundary should feel, magnetically speaking, like stepping from one room into a completely different one. When Voyager 1 crossed in 2012, its magnetometer recorded something nobody expected. The direction of the magnetic field did not change at all. The field just outside the heliopause was pointing in essentially the same direction as the field just inside it. For a while, scientists treated this as a strange anomaly, a possible fluke, because they only had one crossing, one data point, one specific place and time to judge it from. Maybe, some researchers reasoned, Voyager 1 just happened to cross at an unusual spot, where the fields lined up by coincidence. There was no way to know for sure with only one machine's data to look at. Then, Voyager 2 crossed the boundary in an entirely different location, on the opposite side of the solar system's bubble, years later under different conditions, and its magnetometer recorded the exact same thing. The magnetic field on the outside lined up with the magnetic field on the inside. Two separate spacecraft, two separate crossing points, years apart, and the same fundamentally surprising result. That is not a coincidence anymore. That is a real, confirmed feature of how our solar system connects to the galaxy around it. And it is something the models built before Voyager reached that boundary simply did not predict. The sun's magnetic influence and the galaxy's magnetic field are not cleanly separated the way scientists assumed. They are, in some way, researchers are still working to fully explain and connected. Think about what that actually means for a second. The boundary we call the edge of our solar system isn't a clean wall separating two totally different magnetic environments. It behaves more like a filter or a membrane, where the field on one side somehow influences or aligns with the field on the other. That single repeated observation forced a real rethink of how the heliosphere interacts with the rest of the galaxy. because it suggests the two systems are more linked, more porous, and more interconnected than anyone had modeled going into these missions. And speaking of porous, that brings us to the next thing. Voyager 2 found that Voyager 1 simply was not positioned to see. Voyager 1 crossed the Heliopause near what scientists call the nose of the heliosphere, essentially the leading edge of the bubble, often the part pointing in the direction our entire solar system is moving through the galaxy. Voyager 2 crossed on the flank, more to the side, and the region Voyager 2 passed through looked meaningfully different. It appeared, in the words used by the researchers analyzing the data, more porous. That means the boundary in that location wasn't a hard line at all. Solar wind particles were found, leaking out beyond where the official crossing was recorded, and interstellar particles, including high-energy cosmic rays from exploded stars far outside our solar system, were detected leaking inward before Voyager 2 had technically left the bubble. The border was blurry, permeable, breathing in both directions at once in a way that the clean, one data point picture from Voyager 1 alone could never have revealed. This is the moment where you start to see why having two spacecraft mattered so enormously. If NASA had only ever gotten data from Voyager 1, we would have a single, specific description of one exact point on the edge of our solar system, taken at one exact moment using instruments that couldn't even measure some of the most important properties directly. It would be like trying to describe an entire coastline by only ever visiting one beach once in poor visibility. Voyager 2 gave us a second beach, visited under clearer conditions, and what it showed proved that some of what Voyager 1 found was real and consistent, like the strange lack of magnetic field rotation, while other things, like the sharpness and heat of the boundary itself, and the leaky, porous nature of the edge, were completely new information that reshaped the entire picture. There is a reason this matters far beyond scientific curiosity, and it comes back to something that affects every single person watching this video, whether you've ever thought about it or not. The heliosphere isn't just an interesting bubble floating in space, it is a shield. It blocks the majority of high-energy cosmic radiation, the dangerous particles thrown out by exploded stars across the galaxy, from ever reaching the inner solar system at full strength. Earth, and every living thing on it, exists inside that protective bubble. If that shield is more porous than we thought, if it leaks in ways the models never predicted, if the boundary behaves less like a solid wall and more like a breathing membrane letting particles pass in both directions, then our understanding of exactly how well protected we actually are needs to be re-examined from the ground up. This isn't science fiction. This is the actual published conclusion researchers have had to sit with since comparing what both Voyagers found. Now, let's bring this into the present, because the story is still unfolding right now in 2026, and the clock is ticking in a way that makes this urgent rather than historical. As of the start of this year, Voyager 1. For one, was sitting somewhere around 15.5 billion miles from Earth, and it is on track to cross an unprecedented threshold in the middle of November of this year, becoming the first human-made object ever to reach a full light day of distance from our planet, meaning it will take a full 24 hours just for a radio signal to travel from Earth to the spacecraft, one way. Voyager 2, still trailing behind, because of its longer planetary tour decades ago, currently sits around 13.25 billion miles out, with a one-way communication delay of nearly 20 hours. Voyager 2 isn't expected to reach that same one light day milestone until roughly the year 2035. Both spacecraft are also running out of power, and this part of the story deserves to be understood clearly, because it's not dramatic exaggeration, it's basic physics. Both Voyagers are powered by radioisotope thermoelectric generators, essentially containers of decaying plutonium that produce heat, which gets converted into electricity. That power output has been shrinking every single year since launch, and it cannot be refueled or repaired from 15 billion miles away. NASA's engineering teams have spent years carefully deciding which scientific instruments to shut down and in what order, squeezing every last bit of value out of a shrinking power budget. Current estimates from the mission team suggest meaningful scientific operations on both spacecraft will likely continue only into the early 2030s, before power finally drops, below what's needed to keep any instrument running at all. Which means the window we have to actually resolve some of these open questions, the exact nature of that hot, sharp boundary layer, the reason the magnetic fields align instead of shifting the way models predicted, the full extent of how porous and leaky the true edge of our solar system really is, that window is closing, and there is no mission currently funded that will replace it anytime soon. If a new interstellar probe were designed, funded, and launched starting today, using current propulsion technology, it would take decades just to reach the boundary. These two aging machines are already sitting inside of right now. For the foreseeable future, Voyager 1 and Voyager 2 are the only real-time eyes we have on the space just beyond our own sun's protection, and every year they have less power and less capability to keep telling us what's out there. There's one more layer to this that most coverage of Voyager skips entirely, And it's worth slowing down for, because it changes how you should think about everything else in this video. Scientists still don't fully agree on what causes that hot, compressed boundary layer Voyager 2 detected, the one running between 30,000 and 50,000 degrees Kelvin. The leading idea, the pileup effect, where interstellar material compresses against the outside of our solar bubble like snow in front of a plow, is the most widely accepted explanation right now, but it isn't the only one on the table, and researchers have been careful not to treat it as settled fact. Some of the data suggests the heating could also be influenced by the way charged particles interact with the magnetic field right at that boundary. The same strange alignment we just talked about, which would mean the temperature spike and the magnetic mystery aren't two separate puzzles. They might be two symptoms of the same underlying process, something happening at that edge that current physics doesn't have a complete answer for yet. And here's why that unresolved question actually matters for the future of this entire field of research. Distinguishing between these explanations requires more direct data, ideally from multiple points around the heliosphere at once, not just two single crossings separated by 6 years and positioned on opposite sides of the bubble. Right now, there is no mission in development that would give us that. The two Voyagers, aging, losing power, and shutting down instruments one by one, are still the only real-time source of information we have about this exact question. Every year that passes without a new interstellar mission is a year where this specific mystery, sitting right at the edge of our own solar system, stays unresolved by default, not because scientists have stopped caring, but because reaching that boundary again would take a spacecraft launched today several decades just to arrive. Here's the piece of this that I think deserves to sit with you the longest. Scientists built detailed models of what the edge of our solar system should look like for decades before either spacecraft actually got there. They were serious, peer-reviewed, rigorously tested predictions built by some of the smartest physicists working in the field. And when the actual data came back, first from one machine with broken instruments, giving an incomplete picture, and then from a second machine with working instruments confirming some things while completely overturning others, the honest answer researchers have had to give is that the boundary is more complex, more dynamic, and more surprising than anything built on paper predicted. That's not a failure of science. That's what science is supposed to do. It's supposed to send something out to actually check and be willing to rewrite the story when the universe answers back differently than expected. And that's really what this whole comparison between Voyager 1 and Voyager 2 comes down to. It's easy to treat the first discovery as the final word, especially when it makes headlines and gets celebrated as historic. But real understanding often depends on getting a second look from a different angle, with better tools, before you can tell what was actually true and what was just one snapshot from one specific place and time. Voyager 1 opened the door. Voyager 2 walked through it from a different direction, and in doing so, confirmed some of what we thought we knew, while quietly forcing scientists to rethink the rest. Somewhere out past 13 billion miles right now, a machine built with 1970s technology, running on less power than the light bulb in your refrigerator, is still moving, still transmitting, still telling us things about the edge of everything we call home that no model on paper ever fully predicted. And in a few years, both of these machines will go silent, and whatever they haven't told us yet may stay unknown for decades until humanity builds something else brave enough and patient enough to go out and check again. If this kind of story is exactly what you come here for, subscribe and turn on notifications, because we go deeper into stories like this all the time, and you don't want to miss the next one. Let me know in the comments what surprised you most. The hidden gap in Voyager 1's data, the sharp hot wall Voyager 2 actually found, or the fact that our solar system's magnetic shield might be leakier than anyone ever modeled. And if someone in your life would find this as fascinating as I hope you did, share this with them, because stories about how much we still don't know about our own cosmic backyard deserve to reach more than just the algorithm's usual crowd.